Welcome everyone to the Monday evening lecture for 4377. I was just hearing some music online and I couldn't tell whether it was Bollywood or reggaeton. And it reminds me that when I was in Germany this summer with 25 other professors from this University of Mexico, you know, young 20-year-old guys there are like they are in lots of places, right? They have the windows rolled down, the music turned way up, showing off for the girls and stuff. And one of them came by and was playing reggaeton. And all the professors are like, ah, he's like, what did I do? You know, freaking out. Like wherever you go, you recognize that beat. You may notice I sound a little different today. I've got my radio voice. I'm preparing for the Super Bowl. Actually appear to have, my doctor thinks, bronchitis. So we'll see if I can make it all the way through. I made it through the last hour and a half okay, but I may have to stop once in a while for a second and take a little sip of something. But I came here straight from the doctor, and I'm like, please, not now, not during the marathon of 15 weeks of teaching. Okay, so today we are working in Lecture 3. How's the homework coming? Done? Is it? Was it doable? Did you guys use your group chat stuff? A little bit? Use it more? Does it help? Okay, so I'll tell you which of those problems will be on the midterm, just like I always do. So just make a note. I get it. We're all there. If you leaned on someone for help on one of the problems, one of the kisses of death is if you go, oh, okay, that's not so hard. I get that. All right, okay, I can see it. And then it shows up on the exam, and you have absolutely no idea whatsoever of how to tackle the problem. So actually working through it is always different than watching someone else work through it. Just like with riding a bike or cooking spaghetti. It's just never the same if you're doing it yourself versus watching someone else. Right? Yes, sir. Okay, so the question is which packet number? So what you should see in your version of Wireshark, if I catch a few slides, is your packet number on the left. If you don't, you may have hidden the column. You can move them around. You can shrink it till it disappears. It's totally customizable. No two people's stuff will look the same. Did the HTTP Wireshark Lab, I can't remember if it's this one or a different one, does it teach you how to pull a copy of your TLS key to your desktop? Okay, so we had an interesting conversation before the class, and it reminded me there's a cool lab that I need to try to go find that will let you go to your command prompt and fire up a TLS negotiation with another web server, but keep a copy of the key in a file, which normally just is stored by the browser only and used only for the duration of that TCP connection. With that key, you can decode all of what's in those packets that look like gibberish right now. So it's on your computer. It's not capturing the key with Wireshark. It's just running the program from a command line prompt to start the browser and spawn a copy of the key off into a file. There's also some Wireshark hacks that you guys can find that when you're using your phone in tethered mode back to your laptop, you can Wireshark what's happening on your phone. It will not capture what's going over the cellular signal, but it at least will capture what's going over Wi-Fi, or in this case, a serial connection. You can always capture stuff on Wi-Fi, depending on the type of connection. So, yes, sir. Yeah. For file 2, there's 2 questions that we can and we did do for follow for file 1, but no matter how many times I do my add, you're not alone, right? Some of you also didn't see if modified since in your traces. Yeah, not everybody saw those. So this is an example of where the tools are a little bit flexible, and it's very dependent on your operating system as well, and the browser, and on and on and on. So it may be that it's cached somewhere along the way, or your system requires caching a copy of it locally, and it won't bother asking it because the caching server will ask for you, and it tells your system not to bother, or so on. So it's getting hopelessly complicated. And when we get to web caching servers, you'll learn a lot of stuff that'll make some of the mystery evaporate for the way we get web pages. So what percentage of the time do you think when you download a web page, it comes from that web server? Yeah, like less than 1% of the time. So most of the time it's coming from someplace in an intermediary state. You can turn that off if you got that kind of money. If you're willing to put that number of servers up and handle that kind of load, with everybody coming at you. But there's reasons why you don't want to do that. Number one, it slows it down. If everyone has to beat a path all the way to wherever you chose to put that server, it may be close for some users, but it isn't going to be for most of them. The second thing is it's safer, because if somebody starts to attack your web server, it's not the one and only. In fact, we'll talk this semester about how these denial of service mitigation companies will step in the middle of an attack and take it in the back for you, so you can be back up and running. There's a super good example of it with GitHub that happened just last year. That is kind of the best advertisement ever for one of those companies, because they suffered the worst attack volume-wise in history and were out of the woods in 10 minutes. So it was like, took all the fun out of it for someone. Just took it all. Okay, any questions on Wireshark? Okay. So if I look like I'm shivering, et cetera, et cetera, et cetera, it's not the flu, okay? He swears like it's not the flu, so. Yeah, we don't, and I've got a little sanitizer thing attached to my backpack, like after I touch anything. Okay, so we're gonna continue on. We've talked about defining the components. Remember, everything hanging off the edge of the network is just a piece of fruit as far as the tree of the internet is concerned. It doesn't differentiate between servers and phones and tablets and laptops. It doesn't care. They're all hosts. The protocols for communication are between pairs of those, typically at a time. The network's job is to facilitate the communication in the middle, right? So that's an important model. I'm going to introduce another idea today that is contrary to what you may think. It's also not taught in our book, but I found it served students well. You should think of putting a router in a network not when you want to join two networks together, but when you want to separate them from each other. If you always take the attitude about the job of this router is to separate traffic from one side to the other, it will help you guess right on lots of protocol questions. So you should assume that the packet will not be going to the other side of the router as your default. Okay, so we're going to look at some measurements today that govern the experience that your user is going to have on your network. The first is that there are buffers, memory inside routers, where because we have lots of lines coming in and lots of lines going out, there could be a queue. Everybody could be trying to leave over the same route for a moment. And there's even an RFC to tell you how much memory you should have in your router based on the connections and the speeds. And you may not ever read it, but you may ask for a vendor to certify that they follow that RFC. So there's some stochastic analysis that gets done and Poisson distributions to figure out kind of what goes. I've showed you the packet arrival and departure animation, right? 500 packets, okay. I just want to make sure I didn't somehow dream that I did that. So packets are going to queue up, they're going to wait in turn. What happens when this buffer gets full? Yep, someone must die. No more internet for you, come back 2 years. Right? Sort of like the soup Nazi on Seinfeld. So there's a lot that goes into trying to figure out who gets dropped, and the rules inside a company are far more sophisticated than they are on the internet itself. So think about the internet as kind of the bare bones, lowest common denominator, and everything we do inside of an institution is far more sophisticated. Exactly the same routers, same manufacturer, a version of the same code, et cetera. Okay, so here's a packet that's being transmitted. It has some delay due to the fact that you can't put all the bits on the wire at the same time. And you guys know that. What's that delay called? Transmission delay. And I lost the joke that somebody sent me this summer of transmission delay. it basically showed a network person in their car and they couldn't get it out of gear or whatever, and transmission delay. We struggle, really. We really struggle. The jokes suck, but we try. If you find any good ones, there's another professor I work with, and he has this awesome collection of T-shirts. Except I will never wear a T-shirt into class. But he has like Run DNS instead of Run DNC, and 1,000 other ones like that. Like, where do you get these things? Because I ordered them. So packets will queue up. Then you have queuing delay, which can be processing delay and the queuing itself. Processing, hopefully, you have very little of that because it won't take you very long at all to figure out what the address is and what you need to do with it. So hopefully you'll figure that out. So what happens inside the router is queuing and processing. You're going to count transmission leaving and not coming in, and you'll count propagation, which is a factor solely of distance, as you guys know. So transmission delay and propagation delay are totally different. Is that like crazy clear to you guys? Would it help anyone for me to kind of go over that a little bit more? It's super critical that you have a super clear understanding of that because it'll throw you on lots of stuff. So here's my router, and I have a packet with lots of bits in it, and I need to send them on the wire. The ability of me to transmit these 1s and 0 patterns depends on whatever EE standard the designer came up with. But one of the measurements that's really critical is how many bits per second can I transmit. If you tell me that and give me the size of your packet, I can tell you how long it'll take it to get all the way on the wire. I won't have any idea where the first bit is when the last bit's finally making it on there. It may still be on the network as well. It may have long since arrived at the destination. It doesn't matter. That doesn't change the transmission speed. So when we talk about how fast a network is, that's what we're talking about. How long does it take for me to get my packet onto the wire? So it's a sine wave, and you listen to it, and it's a carrier. Think about your radio station. If you are out in the country, you hear static on the radio. If you tune in, get close to a station, your radio will kind of lock in on it, and you'll hear something, even if they're not talking, even if the CD stopped for whatever reason and it's not playing anything, it's obvious there's still a signal being transmitted. You're not hearing the static that you hear when you're out in the country. It's maybe like the background hum of the radio station. So that's an example of you're hearing the carrier frequency, and they're not decoding any useful data off of it. So if you can figure out how to encode your 1s and 0s on this, then you can do it. This year it takes you this long to do 100 bits. Next year it takes you this long. Next year it takes you this long. Then you're improving the bandwidth of the network. Once a bit gets on the network, it takes the same amount of time as any other bandwidth network to travel across the wire. It's a function only of how long the wire is. Because regardless of how long it takes to encode the electrical signal, it travels close to the speed of light. Copper is copper is copper. It's not going to change speed just because you're using one way of perturbing the sine wave versus another. It'll go close to the speed of light. So that's propagation speed. The only thing you need to know for propagation speed is how long is the network. And you can assume in your career that 2.5 times 10 to the 8th meters per second is a decent roundabout number. The book, I think, likes to use 2.8. That's okay. Just something. You can pick something. But that's not going to change. If somebody figures out how to change it, come talk to me first. Okay. All right, so here's the 4 sources of delay. Once I decide I want to get this packet onto this link, I have to wait my turn until I'm in the front of the line, just like at the cafeteria. That's my queuing delay. Then I begin transmitting my first bit to the last bit. That takes whatever time it takes. It's based on transmission speed. And then each one of those bits is traveling at close to the speed of light across the wire. So it's a little bit weird, but we only count the transmission delay on the sending side. We don't add it again on the receiving side. We just don't. Okay? Because Once the last bit gets on and you finish counting transmission delay and you add propagation speed to it, you're covered. You got it. So packets will ride tail to tail, piggyback right next to each other. So as soon as the last bit of one packet arrives, the first bit of the next packet arrives, right? No delay in between. So as long as there's no queuing delay, there's no processing delay, then your packets will enter the next leg of the network right behind each other again, until you get to a point where you run into buffer or you run into a network that's slower. If you run into a network that's slower and there's nothing on the network, you send two packets back to back. The first one begins transmission, it's on the wire. The second one is right behind it. They arrive at the router, still no space in between them. The first packet could be transmitting while the second one is still being received. I mean, as soon as they figure out what they want to do with it, they can begin transmitting it. If that network is slower, there will still be some of it left, still trying to get out the door by the time your whole packet shows up. Does that make sense? So if I'm two mice running through a maze and I get to a hole and the mouse in front slows down because he's got to squeeze through the hole, your view is never going to change. You'll see his rear end until he's gone. So slowing down is an example of going to a network that's a little slower. So you're guaranteed of having some delay because of that, and it's transmission delay in that case. Okay, so you'll have some problems to kind of play with that. The book has a really good analogy with caravans, and what they basically look at are a series of toll booths, a number of cars, and they propagate or drive 100 kilometers per hour. Right? They make their way across the network. Once you get to a toll booth, it takes 12 seconds to process you. Take your money, give you the receipt, the arm goes up, and you can begin transmitting onto the network. So we'll roll all that into 12 seconds. So it's 100 kilometers and then 12 seconds, and then another 100 kilometers and then 12 seconds. So if I have 10 cars, we can calculate how long this ought to take. But let's start with just the second car first. The first car leaves. He's driving at 100 kilometers per hour, so it's going to take him 60 minutes to get to the next toll booth, right? It's going to take him an hour. It's 100 kilometers, and he's going 100 kilometers an hour, 1 hour. How far behind him is the second car? 12 seconds. Just that simple. So that's as close to back-to-back as we can get them. What would we need to change if we wanted them to be closer to each other? The processing time at the toll booth, which is what kind of delay, might you say? Transmission, maybe queuing delay. The third, fourth car, they're going to be complaining, honking their horn. So, yeah. You also could slow the bandwidth down, but I told you that's all rolled into the 12 seconds, so that's not going to work in this example. All right, so good, 12 seconds. So the entire caravan of 10 cars, therefore, is going to take 12 seconds for the first car. Immediately, the second car begins to send. It takes 12 seconds. How long for all 10? How many minutes? 2, and the 60 for the inter-toll booth distance? 62 minutes. Okay, now suppose they drive a lot faster, 1,000 kilometers per hour. So how long are they going to take to go 100 kilometers now? 6 minutes. Yeah, I'm jealous. That was a little hard for me. I had to wrap my head around that. Really? Is it really 6? 100 and then 1,000 in an equation gives you 6? Yeah, I know. It's like tough. Yeah. So, what can I say? So if they go 1,000 kilometers per hour, it's only going to take them 6 minutes. But the toll booth still takes the same 12, right? 12 seconds. So 6 minutes for the first one, plus 10 times 12 seconds for all the 10 cars to make it through. So after 7 minutes, first car arrives, and so forth. So you'll have a problem to kind of work through that. One of the things that we're kind of hinting at here is traffic intensity and queuing delay. So everyone knows the bottom right picture. We all live that, living in Houston. But mathematically, it's exactly the same behavior that we pattern on data networks. It's stochastic probability, and it's a distribution of packets, basically. And it's used in other types of systems as well. A biologist in my class last semester pointed out it's used in life systems. How many of the cells need to pick up the drug in order for the patient to receive the treatment? It doesn't need to be all the cells, just enough of them. So if I have my bandwidth in bits per second, and I've got the size of my packet in bits, and you tell me the average arrival rate, that's the new variable I'm adding here. It was L over R before, but now I'm adding an A to it for the average arrival rate. If that ratio is close to 0, then it means your ability to transmit the packets far exceeds, is a much bigger number than the size of the packets and how often they show up, LA. That's kind of what you want, but it's not what your network manager wants. I still remember when Dave Gutierrez, who's a biomathematician at MD Anderson, when I was in college with him, he, I think, was a civil engineer. I think that's right. But he told me civil engineers don't build roads to relieve congestion. Idiot. They build roads to create congestion. I'm like, what? He goes, yes. You build roads where you want people to go. So you build them so that they're busy because you're channeling commerce down a certain path. And I'm like, you're going to blow up my brain, stop. I don't, that's not, so it's supposed to be congested all the time? I keep hoping that maybe someday there's like light at the end of the tunnel. And he goes, nope. So network managers would totally agree with that. They want their networks to be busy. Otherwise, you're wasting money. So you want it to be full as much as you can. So the closer your average gets to bigger than, approaches 1, basically, your delay gets large. And when it's greater than 1, then you have the picture in the bottom right corner. It's like closing the freeway. They arrive faster, 0 are leaving. It's easy to figure out. You're going to have a problem with that ratio. Okay. So one thing that's not obvious about that, what did I do with the stylus? Did I drop it? Wow, I had it a minute ago. Oh, I put it in my pocket. Nervous. You'll notice this never reaches that ratio of 1. This curve never quite touches the point at where your ability to handle packets coming in is a perfect match for the bandwidth going out. And we saw that last time. When we set the animation to equal on both sides, we still had packets build up in the queue. And we still had them get dropped because of the distribution that they have. Okay. So with the internet, we have some tools that we can use to kind of help figure out what's going on. One of the things that we can do is send a packet out on the internet that, like all packets that leave the internet, has a certain number of hops that it's allowed. Routers don't remember the packets they've seen, so if there's a loop, it will never know. It's not going to figure out that it's seen the same packet for each of the last 15 seconds for an hour. It's just not going to know it. So the way we prevent packets from being sent around in loops, which is bad, is we give them a hop count. And it's reduced by 1 with every router that's visited. And if a packet ever gets down to 0, then it's dropped off the network, and an error message is sent back to the original sender to let them know, hey, I killed one of your packets. So this is a network management feature that we've hijacked to trick routers into revealing their identities. So we normally don't have any idea how many routers a packet goes through between the source and the destination when you go to, say, google.com or Microsoft or wherever. So what you can do is send out a packet that has a hop count of 1. It will get as far as whatever the first router is towards that ultimate destination, and that router will drop it and send an error message back. When they send an error message back, it has a source and destination address. The source address is that of the router, right? Now you know the address of the router. And you can now send a packet towards the same ultimate destination with a hop count of 2. It will make it through the first router, just like every other packet would, and it'll get dropped by the second one it will send an error message back, and now you know its identity. So there's a program called traceroute that does exactly this. It continues to send packets with incrementally increasing hop counts, 3 of them at a time, so we can get kind of an average of what's going on. And we try to get the network to respond back. The result of running a trace route, which might be trace RT or trace ROUTE, depends on how it's spelled, and it's built into lots of other tools. Lots of websites give you a web page where you can initiate a trace route, for example. They basically look like this. The number on the left shows you the hop count when the packet left. So when I send a packet out with 1 hop left, this is the router that complained. CS gateway at whatever this IP address is. And those packets took 1, 1, and 2 milliseconds respectively round trip to get back to me. All right? And then the second line shows at UMass, third one's at UMass, fourth one's on a different site. So you can basically go through this. If at some point you kind of know where you're going and you see a big increase in delay, you can safely assume it's a transcontinental link. Here are a couple of entries where, for whatever reason, we don't have responses coming back. Why do you think that is? Does it mean there's no 17th and 18th router? It's ignoring you. Exactly. Yeah, so router manufacturers, they're on to us. And router managers. They don't really have an interest in having us know about their routers, because then it's an attack vector. And we can try and swamp it, and etc. Try all known public vulnerabilities to see if the router administrator has bothered keeping up with all the patches, etc. So there's rooms full of people that just try hacking into every single router every single day like this. And those routers near the end have been programmed to ignore these particular types of packets. Well, it's easy to do that because these are a very specific type of packet. It's an ICMP echo message, better known as a ping. And if you can't get ICMP echo to respond, just send a different kind of packet, any kind of packet, email, web page, time of day, whatever you want. Just set the hop count to whatever number you wanted, and it will drop off at the right spot, and they have to respond to the others. They have to tell you that there's an error with your packet. So if they're going to blow you off with ignoring ICMP echo packets, then just send them a different one. You know, send it in disguise. So typically, the experience of using traceroute is pretty miserable. So if I try to traceroute, for example, to this website, most of the time what you're going to get is kind of bad. Let's see if I can make this a little bit bigger. And then you do have to spell it right. Okay, so I'm doing one to Mexico on the right, doing one to Rice just up the street on the left. And they both leave via this server called Marconi, NNM, whatever that is. You know, it's probably the name of a building on campus, but it's the same one that's over here. And this one was able to guess the name of the system, and this one had some sort of weird issue. It only got two of the 3 packets back. Okay, so this one's finished. This one is not. So let's go look at this one and dig into it a little bit more. So there's some routers in the middle that didn't bother to respond. So my packet, when I sent it out with 1 hop left, it made it as far as this device. With 2, it made it through this one, presumably. The route could change, but presumably it made it through this one and got stuck here. This is PGH, which is what? It's our topside building, right? HA0, probably high speed, port 0, fast gateway Ethernet, rack 1, slot 1, port 7, something like that. So Charles Chambers guys can tell exactly where to go if they see problems cropping up. Then it goes to Vespasian, and then to PBR FG wireless. So this is probably the point where all of our wireless packets are concentrated. Then it goes to Southeast Texas Gigabit Network and makes it over to Rice. There's a location on the Hardy where we apparently have some sort of asset. I think it's probably a phonoscope or an old GTE central office building. And you can look up some of these addresses and see who owns some of these, but some of these are network number 10. So this tells you this whole thing is private. You can't have 10 dot addresses in the middle of the internet. So this is all just between us girls, between us and Rice and Texas A&M Biosciences Institute and Baylor College of Medicine and a few other places. And it is. Meanwhile, what happened over here? Well, apparently the wall is keeping my packets from going through. So I have some that have made it. Things went the way they were supposed to for a while, but they changed at step number 8. The 8th hop on the left was to a Rice device. The 8th hop on the right was not. It's to someplace else. These are indications that it's going through Houston. Where's this? Yeah, and then where's this? Tucson. Where's this? Phoenix. And it'll get on to Internet 2 at that point. Then it comes to here. Where is that? Equinix, the big data center we looked at the picture of. It had all the strange, like no cars parked around it. And so this building, this one is not that building. It's the one downtown that sold for just an exorbitantly high amount of money. But this one is all the way in Los Angeles. So the first thing you notice is this packet's doing this. Houston, El Paso, back to Tucson, Phoenix, then I think one place I convinced myself it was coming back this way, and then continues on out to Los Angeles. Then a whole bunch of hops, all in the same network here. So notice these are all number 15. So they're all number 15 because what this is telling me is every time I sent my 3 probes out, I send 3 to kind of average the time, a different router responded each time. So this is a highly diverse point on the internet, where they have lots of routers handling routes along this path. And then the same thing happened with 16 and 17 and so forth. So lots and lots of redundancy. And if it ever gets down to the end, I think we'll find it goes through McAllen, Texas, or Tijuana. Those are the 2 fiber routes in, from Tijuana to Mazatlan or from level 3 to Monterey. And it also depends on where the server is that I'm actually trying to trace route to. Just because it says uh.edu on the end of it doesn't mean it's on this campus. Where can it be? Where can you put that server? If it ends in uh.edu, where do you have the liberty of locating it? Go for it. Anywhere. Anywhere. Absolutely anywhere. You can pick off one address, one name, and park it someplace else. You can park just www.microsoft.com with a totally different provider than every other host at Microsoft.com. Usually, if you try to open a web connection to just the last 2 parts of a domain name, like Microsoft.com, they will assume you really meant www.microsoft.com, and they'll redirect it, because it's usually not the same machine. So if we want to see this, let's pull up a trace route to Microsoft.com. Warning, Microsoft has multiple addresses. I'm using this one. So they pulled up the DNS record. We'll talk more about that later. So far, I'm getting the rude treatment from my own wireless network, and we'll let that run. So I'm going to change things on you, and now I'm going to go to www.microsoft.com. Totally different. Do you see that? The very first line tells you that when you look up the address for this computer, in order to know where you are trying to trace route to, it is registered in the Internet's database as a server belonging to a company called, owning the domain name, Akamai Edge. Have you guys ever heard of Akamai? Yeah, in the homework, right? So yeah, you should all have said yes, just for the record. It was in the homework. So Akamai is a overlay provider. They're very sophisticated. They do lots of stuff now. But what they do is stop all traffic trying to go to that server before it can get to Microsoft. And Akamai is a big enough provider that they actually have thousands and thousands of servers and ISPs all over the world. So the chances are really, really good that you're like 1 millisecond away from some Akamai server on Earth at all times. So if I want my web page to look like super fast, I give a copy of it to Akamai, tell them to push it out to their servers, write them a check, and they'll answer as if they're Microsoft. You just feed them the content. It's all automated. It's just coming from a local server. It doesn't have to come from www.microsoft.com. Said differently, that's exactly where it's coming from. It is coming from www.microsoft.com. It just happens to be a different server than you think. Millions of dollars a year. So next time you download software from Microsoft, pull a trace route up for a second. Pull Wireshark up. Grab a few packets, and you'll see it's not going there at all. It's going someplace completely different. So who do you think is the dominant user of this technology? Whose business would never survive if they depended on having to use internet infrastructure that hauled everyone's packets all the way back to their data center and pushed all the data that they wanted all the way back out to their computer. Napster's a decent guess. And Google's got their own data centers. They have an overlay network as well. I'm talking about orders of magnitude more data. Sorry? No? No, more. What are you going to do tonight at home? Netflix. Netflix accounts for over half of the traffic on the internet for access networks during prime time in the United States. Yeah, so, you know. So somebody at home opens up a link to Netflix, and it's not going to come from Netflix. In fact, would it surprise you to know Netflix doesn't own any computers to speak of? They don't have a data center. They rent servers at Amazon to compress the movies that they get into all different sizes and shapes. And they have a running competition between 3 content delivery networks on a per city basis to see who can deliver things with the least dropped packets and errors and best response and highest rating. And Limelight, Level 3, and another. So it's an overlay network because it goes the same places at the edge that the internet goes, but it doesn't run over the internet at all. So from the time you pull up the web page at Netflix and you click the movie you want, it's coming from the local server at your local ISP in Houston. If it's not there, they have their own overlay network that is big enough to ship the whole movie in a few seconds from their data center out to that server and then start playing it for you. All right? So if you're not using a distribution method like that, you're going to have a hard time competing. So the thing that's interesting is there's such scale now with some of these high-end solutions. It's hard to imagine how people will continue to compete and innovate. There's some good counter examples like Uber or Lyft or Waze. Waze is a good example because it does have to go back to a central location, or at least regionally, because it can't, just send you to the local one just in Houston unless they are renting actual servers. So it's very hard to find out information on this stuff. If any of you do interns at one of these companies, please come talk to me and share the stuff that you can. especially if there's any graphics that you know that are on their website that I would never find, and let me know, and we'll use it to improve the classes. Okay, interesting? Okay, did you know this already? All right, good. Okay, we kind of got lucky for a while. This is typical. This is typically what you get. You get the middle finger from traceroute because nobody wants to answer your traceroute messages. If you're running Windows or Linux, you can change the type of packet that it sends to force it. But if you use Wireshark to find them, they won't look like ICMP echo messages anymore. You will be sending something else, an email message or network status message or something like that. Right? So you just have to be aware. I don't know that maybe the Mac will do it too. I don't know. Okay, let me quit out of that. There's some really interesting ones I've done, which is, one of these days, if I were to go through it, I would probably find lots of things that people wished I didn't have, like here's an ARP storm. Let's see, Cisco, Mexico, both named through those wildfire. Okay, let me find the one here that I want. Intercable. So there's one in here. What's the name of the German airline? Lufthansa. There we go. So here's what I grabbed on my Lufthansa flights after the service was discontinued. So there's probably some fun stuff in here to kind of go through and look at. But you can run Wireshark on the plane. No one will know. You can grab packets and see what people are doing. In fact, you can use this maybe you can't use it to see what's in the packet, like the data that's being transmitted, but you can at least see the URL. Isn't that all you need? I mean, if you have a suspicion and you can find the URL, now you know, right? Okay, so so you got to be careful because there's bosses that will look at some of that stuff too. Like, are you interviewing with someone else? Do you not love me anymore? So I mentioned there's a couple of other ways of doing trace routes, and you can put a web page in front of any program you want. One program you can put a web page on top of is traceroute. So here's somebody that built a web page, and they are offering to run a traceroute from their computer, wherever yougetsignal.com is located, to whatever claims to be google.com. And so I'll trace it, and we'll see if we get anything out of it. And we may not. And these sites are infamous for going down all the time. They're just totally unreliable. So let me see if I can get something else in here. Then we'll go to Amazon. So we'll give that a little bit of time to see if it draws something. The nice thing about this one is it will look up the latitude and longitude that the router owner is obligated to register with the Internet Assigned Numbers Authority as the location of the router, which they don't. And it will try and draw you a map of where your packets are going based on that. So people are not good about doing that. Lots of people have very good reasons for not doing that, and they never will do that. So the CIA is probably not going to publish the latitude and longitude under the Onion Dome in Moscow of one of their routers. It probably would be a big attention getter. Okay, so packet loss is when something arrives and it's full. You don't always just want to drop the packet at the end. Sometimes you want to be more sophisticated than that, and you want to drop a packet based on some other criterion, like, is it very delay sensitive? Or is it from a user who didn't pay as much for their level of service? Or did I just drop one of theirs last time? So you can round robin and try to make that fair. When you're going from a small pipe to a big pipe, life is good. Right? This is like going from your driveway onto the big wide empty road. Life is great. Where problems happen is when it's in the other direction and you're bottlenecked. So when you're looking at a network and you're asked what the bottleneck is, it's super simple. It's just the slowest link, period. That's it. That's your bottleneck. So whichever router is connected on either end of that is going to have, the one on the left is going to have an issue pushing packets across as fast as they get there. So that router on the left is going to be dropping packets. Okay, you don't have to calculate stuff end to end. You can just, in this case, look for the one that's not as tall on the diagram. So you get it kind of nice that way. Okay, your throughput is a different measurement. Throughput basically says, on average, overall, how many packets of the user's data am I getting through this network? So sometimes the packet gets dropped and it has to be retransmitted. Don't count that as another user packet because you lost the first one. So that still counts as one of the user's packets that got across. If there's delays, you're going to hold that against yourself, not the user. So if I'm sending a 1 megabyte file, I want to know how long is it going to take to do it. One of my favorite cartoons of all time showed a picture of a guy in the car with the wife and the kids and the dogs coming over the hill in the last few miles to grandmother's house. And he says, you know, I can smell the turkey now. We'll be there in 15 seconds. No, make that 6 hours. No, make that 2 minutes. And the caption reads, going home for Thanksgiving is brought to you by the guy who writes the Windows time remaining code, which is about the truth, right? So your throughput is what you really care about. How long is it going to take you to get this job done? And that's what your users are going to base this on. So instantaneous is an important measure. We will use instantaneous measurements to spot problems on networks. The average is also useful. So what you'll see we do when we're calculating how patient should we be, it's a factor of how busy the network is. And so we're constantly measuring with every packet, how's it going, and adjusting our level of patience up or down accordingly on kind of a weighted average basis. So in this case, what's the end-to-end throughput? What did I tell you? What's your bottleneck? It's the slow one. And the average end-to-end throughput is going to be R sub C in this case as well. You're never going to get stuff across the network faster than your slowest link. That makes perfect sense. So one of the things we've done in the backbone is try to make all of these connections equal in size. That's the fair thing to do. And just try to make sure we have enough of them that if you choose to route a different way, you're not going to run into lots of bottlenecks. You may run into more hops and more delay, but it's not going to be because that other route doesn't have the same bandwidth that this one did. So they work very hard to try and do that. So the bottleneck link is the one that constrains input. Here's a little more interesting example, more real. Here I have a single link that's shared among, in this case, 3 end users trying to connect in some combination or another to 3 servers. And we can say there's like 10 of these. They drew 3, but that's okay. We'll say there's 10 of them here. And so on average, they should each get 1/10 of that bandwidth. Agreed? That would be fair, right? R over 10. But in practice, the bottleneck is going to be one of these other links. So what you want to know is which is bigger, R or some formula that includes R sub C and the probability that they're busy at that moment. So not everybody picks up the phone at the same time. You guys know I like hacking the phone network. So one of the things I used to do as a parlor trick is exactly at the stroke of midnight, pick up your phone and you will not get dial tone on New Year's Day. It's not true anymore, but it was in the old days. So, you missed your chance. I'm sorry. I hate to tell you. All right, so we're going to spend a little time talking about protocols and layers. Have you guys run into the layered protocol stack of TCP/IP before? Has anybody bumped into it? Sometimes some of the other professors will mention it. Okay, so what they basically do is divide the task of getting a packet from your program all the way onto the network into layers, so nobody jumps off a bridge, because it's too hard to write the code end to end. And we want lots of people to use the same modules of code, so everyone doesn't have to write their own. So we built a library of function calls that, as a C or Python or Java or whatever programmer, you can call and you pass it arguments just like any other function call. But the arguments you pass to this are, I would like a connection to this computer. I would like for you to be reliable or not. And here's the data that I want you to send. And that's exactly how data gets across the internet. Every packet starts off like that unless it's an administrative packet of some sort. So it's super simple. And this library is called the socket library. So you're plugging your program into a socket. And there's two different sockets that you'll usually call, one to send, one to receive, and there's two different flavors that are the most common. One will take care of watching over your packets and retransmitting them if something goes wrong, and the other one won't. So can you think of examples of where you wouldn't want it to resend packets that are lost? Well, let me ask you this. Is it going to be when it matters, or is it going to be when it doesn't matter? When it doesn't. So what's an example of a stream of packets that I could send to you where it doesn't matter if some of them get lost? Your paycheck? Your IRS tax return? A video conference call, excellent example. What about streaming radio? Do you care if some of the packets get dropped? Well, whether you do or not, they're gonna. So at least on the internet. So some types of data are perfectly fine with the unreliability that the internet forces on you because it will not provide any type of guarantee whatsoever that your packet will even make it, let alone that it will happen in a certain amount of time. It's an unreliable data transport, totally. The routers in the middle keep copies of nothing. If a packet gets dropped, they usually send you a message, and that's it. Then you got to figure out which packet got dropped and what you want to do about it, and tell your program, or if you're running a certain reliable protocol, maybe you kept a copy of it. So we'll get into those details as we go along. So we've talked about all these pieces, but what we want to try to figure out is what these layers are about. And so the analogy that the book likes to use, which I'm okay with, it's not a bad analogy, is to look at air travel. And you've got people at each layer of air travel that deal with their counterpart. So for example, the ticketing person at one end, when you show up at the next airport and you've got the next boarding pass for the next leg of the flight, you're going to deal with the same kind of person there that you dealt with in the first leg. If you fly internationally into Houston and you go on from there, you know exactly what I'm talking about. You have to go through security again and all that. The person that handles the baggage system, the numbers that they use for the bags, the claim tags that they have are connected in some database to your ticket, but they are not the same number. Your baggage claim ticket is not your ticket number. Agreed? And if you look at the gates, gate numbers are not the numbers on your bags. They change. And same thing with the airline, the plane number, flight number, to be specific, runway number, and the routing that you take. And have you guys used Flight View before? Really? Okay, so my partner drives me crazy because he can look at a plane and tell me where it's coming from and where it's going to. And let me try to pull this up for you. If it's a north-south flight coming from south of Houston, there's only a short list, and it's a big plane, there's only a short list of places it could be coming from. So what I'm going to do is make the screen full. I don't think this is going to end up on... Yeah, but I don't want to do that. I want to make it bigger. How do I make it bigger? Maybe what I do is stop sharing. I don't understand. What the heck is this thing doing? Yeah, well, dang it. I'll just do this. What's this thing called? It was called Photo Group. All right. This is a pretty cool network application. All right. There we go. All right. Pull it back up again. This one I can make bigger at least. Okay. So this is a free program called Flight View. It shows you all the flights that are coming and going. If you touch a particular airport, It will color code the ones that are coming and going specifically from your spot, but I didn't click on it right. I clicked on my location instead of what I wanted to do was click on Intercontinental Airport. Okay. So here are all the flight arrivals and departures. It's hard to see, they're different colors. You can pick one of these flights. Here's a United Airlines flight 2020 Boeing 787-900 to San Francisco. And if I can find one that's landing, it's a lot more interesting because it's ours. Yeah, it's seconds delayed, but yes. Here's one that came from El Paso. Let's find another one here. From San, no, that's not far enough. What about this one? Okay, this one's Midland, Odessa. So let's see where this is. And what I'm going to try to do, I may not be able to figure it out here. You can see at every minute its altitudes, the air traffic control center that was directing it, the path that it took, its climbing or descending speed, and its altitude. Flight aware. The flight view is another one that's out there, but they're pretty cool. And it's a decent network model because they're having to interface several different systems and try to build a real-time display out of it. So this is a hybrid example of where it may be a problem for you to drop packets, even though it's not your paycheck, because you may want to see the data. So if you choose to organize your data this way, there's lots of other models like this that you can use. So why do we layer? So people still want to work in this career. It's too hard to do it otherwise, and modularization makes everything easier. Some people claim that layering is considered harmful. I've seen a senior architect at Cisco stand up in front of the office of the president of another country and basically tell them this idea that you can bury your head in your own layer and only worry about what you send above you and below you one layer, and that's good enough, is dead. You end up with huge security problems if you do that. You have to know what's happening top to bottom. Well, whether you do or not, in your particular job, we're going to learn about all of them. So here they are, applications at the top. That's where 99% of the programs that you run live. When in doubt, guess application layer. Where does ping live? What about the SMTP email protocol? Yeah, you got it, right? So just guess that. Unless you know that it's not, then your guess will usually be correct. The transport protocol is what you hand your data to. It's what gives you access to the socket library. So when you want to hand data to the network, you hand it through this socket library call to software that is running in what we call the transport layer as part of the operating system. So this would be TCP, for example, or UDP. It in turn will do some housekeeping perhaps and assign some mapping so it knows when a packet comes back for you later, it's not just some random packet showing up, it knows to give it to you, and it will in turn hand it down to IP, which runs in the network layer. There's lots of other things that run in the network layer as well, but IP runs there. So things that look at your IP addresses, that try to figure out, okay, you're trying to reach this address, which of the outgoing ports is the best choice for me to send this packet on its journey? That happens in this layer, in the network layer. The data link layer, which is almost always called data link, not just link. It also screws up my acronyms, my mnemonics, when he calls it just link, is the one that's responsible for the physical connection protocol that runs on top of the wire. So this would be Ethernet or Wi-Fi or a dial-up modem, for example. Most of the time, it's joined at the hip with the physical layer because it requires that you use a certain type of cable or a certain type of fiber or a certain type of antenna to operate. So some people put those two together in one. We will not in this class. We will leave them as 5 different layers. So if you remember to call data link, and I will use that 100% of the time, then if you just remember, please do not take advice. Those are the 5 layers. Please Do not take advice. There's another competing model in the world that we don't use on the internet. That's an international standard that this fits into. This is an example of that framework. It's an instantiation of it. But that one has a couple of other layers, session and presentation. So that one is please do not take salespeople's advice. It's a little more biting, you know? What you think? All right, so here's that other one. We'll spend very, very little time on that. So the idea is from the time you hand the packet to a program, let's say the user types in a URL, and so you need to get this message over to a web server somewhere. Your program, your code, has to get to a point where it's going to make a socket library call and hand it off to the layer below. And from there, it just cascades its way down. At each step along the way, the layer takes everything that it's been given, puts it inside of an envelope, and adds any kind of extra information that it needs on top. It may also allocate some local memory to keep copies of things that are going on. But at each layer, you take the whole thing you've been given from above, you change not one bit, you put it inside this envelope, and you put whatever addressing you want on the front. Each layer performs a vital task. We'll look at what each one does so you understand why there's 5 and not 1. But for that reason, the way to draw one of these diagrams is always start at the application, assuming you're running an application, and you work your way down to the physical layer. After all, that's how you leave your computer. That's how you walk across the street. That's how you get to the moon physically. At some point, you have to leave via atoms. So this is where they connect, and Wi-Fi antenna would count. And you'll get over to the next device. Some devices do not implement all the layers. They only implement a subset of them. And when you finally get to the destination, you climb your way back up, opening up envelope after envelope, checking the status, making sure things look okay, throwing the envelope out, digging inside for the prize. And when you finally get back up to the application layer, you should have exactly the same bits that were sent by the application over here. The two applications cannot tell that they were on a network, let alone that they weren't connected directly to each other. That's the vision, the fantasy that we have to provide. So if we're doing our job right, you can't tell that the destination is not on your same computer. That's the idea. All right, so here's a message. I add a little bit of header. It's called a header when you add information onto the front of the envelope. So now I have the message that the application gave me, plus I've added transport header to it. I'm going to continue on down to the next level. I take all the bits I was given, which is the message plus the transport header that I added a minute ago, and now I add my own header. And I do it again, and now I'm ready to send it over a wire. And I'll make my way across. I'll make some decisions on how to send it. When I get to the end, what I'm left with is the same message that was dropped in at the very beginning. So this is called encapsulation. Like a capsule, like a medicine capsule, you put something inside the capsule, or a time capsule. So you don't usually change what's in it. There are lots of counterexamples, but usually that's a security problem if somebody's changing the stuff inside your packet. Okay, so we've already broached this just a little bit to talk about security, but there's a couple of classes of attacks, and it's shifting right now. In the last couple of years, the attention has moved away from the network to the applications themselves, which is a new vector of attack. The field of network security tries to figure out how people are doing this. There have been some crazy tools developed in the last couple of years, maybe 4 years, including one that keeps for in perpetuity the header of every IP datagram that passes by on your network. All of them, every single one. So that later, a month or 2 or a year, when you realize you've been hacked, you can go backwards in time and figure out, now that you know what to look for, of where it came from and when. That's a tool that reduces the amount of time between when you are hacked and when you discover it. Vendors are just now starting to publish those numbers. Cisco published one that was I don't know, 40 days on average, down to 13 days. I'm making those numbers up, but they were depressingly big. We stop with network security maybe 100 billion attacks a day. It's just constant. It's constant. So if you do not keep your system updated, I absolutely guarantee you, you've been hacked. 100% probability. So if you're at home behind a telephone company router, they're your best friend because they give you a private address, which is really hard for people to get to in the outside world. That's why we all have 192.168 as our IP addresses at home. And we'll talk more about those numbers. So Vint Cerf, who along with Bob Kahn wrote TCP/IP and was an early pioneer in the internet, his speeches in the last year or two have sounded to me a little melancholy as he expresses regrets that this seems to be becoming SpaceNet, if you guys are Terminator fans. Thank you. Well, I'm trying. At least I saw it. I'm just happy I got to see a movie. I never get to see movies. It was on the other day, and I'm like, oh, we're not going to change the channel. It's like, I know it's halfway through. So it wasn't the one where the machines are actually alive. This is like the episode before, where they jump into the steel, molten steel. Judgment Day, yeah. God, it's a great movie. So you can listen to him, and he expresses regrets over kind of what's happening. One of the most popular ways of issuing an attack is to do something that looks legitimate, but overwhelms the destination to the point where they don't know who the good users are from the bad ones, but they know that they're being attacked. So let's say you want to do what University of Houston students did in 1969, which is go around to area cafes that would not let black Houstonians sit at the counter, and they would come in at lunchtime and all sit at the counter and order a glass of water. And pretty soon the manager figures it out. So yeah, they're under pressure. Now I get their windows broken or something else, or they can go out of business. Which would they rather have? So that's a denial of service attack. It takes you a while to figure out what's going on. It's effective. So a DDoS attack, a distributed denial of service attack, is one where you infiltrate a number of unsuspecting zombie computers at a given time and place to start sending seemingly illegitimate requests to a target and overwhelm it. Yes?
Would you also have difficult to figure out when you expect the traffic to get in? So, like, let's say, you expect a big amount of traffic to come in, and then it's just more than you anticipated.
Yeah, you should assume that at least half the traffic that you're processing is garbage to begin with. That's kind of the rule of thumb we told people. Half the stuff you pay us to deliver to your router is garbage. And they're like, why don't you stop it? And I'm like, why don't you stop it? You know, we built the network. So people ask things like, why don't you just cut the Russians off? Like, next question. So I don't know that I have a great answer sometimes for some of those questions. But you're always getting attacked, always. You notice it when it's more than you can handle. That's the difference. So what you can pay are back to Akamai again. You can pay companies like Akamai whenever you are being attacked. You can also pay them to shunt the attack to their servers all over the world. They don't go very far over the internet. They go one hop, and then that's it. And they're not really doing anything with them. They don't really care what the request was. They just view it as garbage, and they just shunt it to the ground. So that was a very effective method for GitHub to overcome an attack last year that was at its peak over a terabit per second of packets arriving. So you can put somebody bigger than you in front of you, and they can absorb the blow. Sometimes it's too big for them, in which case you are in trouble. And that happens. So a security officer at a company with a decent network, among other things, now has to worry about what their mitigation strategy is. Do they have a contract with somebody who can help them get out from under an ongoing attack. And it's funny because most of these sites that provide these services that you go to, within about 10 seconds of being on their site, a little chat window pops up and says, "Are you being attacked? Do you need help? We're here to help you. Click here." So they know exactly where their market is. And that's usually when most people decide maybe they need to do it. So here's the idea. You get a whole bunch of computers to send seemingly legitimate packets to a site. And that's a decent stopping place, I think. Let me see. I don't know. We may be able to wrap this. Yeah, we've got a couple of more slides. I'll blast through them here. Malware is something that reproduces itself in the form of a worm or a virus. So if you've gotten emails from your friend that don't make any sense, yeah, they've been hacked. So somebody's gotten a hold of their address book. A worm, on the other hand, takes advantage of a specific vulnerability. So it will exploit your reluctance to stay on top of security patches for your device. The very first attack was a high school kid in '74. We can talk about all of these if you want, but what we're seeing now, and as of 2017, is a huge decrease in network layer attacks and a giant increase in app layer attacks. This one is kind of interesting because there are sites out there that you can pay $25 via PayPal or Bitcoin or even credit cards. They're not shy, and pay them to try to attack your network just to see how bulletproof you are, or your friend's network. So it's cybercrime as a service. And one of these sites actually got shut down recently. I did take a picture of it. Yes, you will know that once you see the picture. The problem is I have too much stuff with these. Yeah. Well, I don't want to go snooping around through all this stuff. But what you'll see if you go to one of the prominent sites now is a sheet of icons of every law enforcement agency you've ever heard of around the planet saying this site's been confiscated. And they're going around shutting them down as fast as they can. But it's hard to do. We're not very nimble at doing it. Okay, guys, I can't believe I made it without falling over with no voice. That's a minor miracle. Say that again? Yes, I'll be online. Are there political issues? Only if servers don't want to respond. It's fair game. Yes, sir.